All right, before I even start with the theory, I want to make sure everybody understands these devices aren't toys. These devices can be very, very dangerous. They can be dangerous loading them. They can be dangerous running them. There's things that can happen later that I'm going to explain in here, that these anomalies can happen, where these devices can produce X-rays, they can produce gamma rays, and they're going to produce microwaves if you get them running. All of which you don't need to have your body radiated with. So, if you get one of these devices running, you're going to have microwaves coming out of it. And you might have a lot of microwaves, not some 100 milliwatts like is in a cell phone. You might have watts of microwaves coming out of these devices. And you might have a lot of gamma rays or X-rays coming out. So I'm going to tell you about some incidents that happened with some people that built these. So next thing we're going to talk about is the actual theory of operation. But you need a Geiger counter. You definitely need a Geiger counter. You need lead shielding. So you can't just, I'm going to put a little bit of isotope in here and it's going to work. It doesn't work that way. So we're going to talk about the theory next. All right. Let's talk about that theory of operation of nuclear magnetron. So if you're a beginner in this and you don't know anything about magnetrons, you need to pick a magnetron and you need to pick an isotope that are relatively close to what the magnetron actually uses. In the case of a microwave oven magnetron, some of them use 2,000 volts, other ones use 4,000 volts. A 4,000 volt magnetron will work better with the isotope Fe55 than a 2,000 volt will. Can you make modifications to them? Yeah, you can make modifications to these magnetrons. Now, somebody's gonna, I know you physics people and you electronics people are gonna go out there, well, there's no ground return. But the basic operation of the isotope is that the magnetron is stripping the electric field, the magnetic electric field of the particle away, whether it comes from a heated cathode or whether it comes from a cold cathode that the magnetron represents. That the electron in the microwave cavity is having the energy stripped from the particle. Now, you have to get particles that are sort of in the range of what the magnetron was built for. In the case of a microwave oven magnetron, a 4,000 volt one, Fe55 has peak 6,000 volt particles coming out of it, but it also has lower voltage particles coming out. There's a bandwidth in there. You have to sort of realize that the voltage level that comes, the particle level that comes from the isotope isn't all high voltage particles at the same level. You have some lower voltage particles and you have some higher voltage particles. And when you get the energy ring that's in a magnetron that forms, that causes the oscillation in it, you're going to have a cloud of particles rotating in the magnetron at a lower energy point than what the high voltage particles are and what the low voltage particles are. You have to realize that this is a spectrum of particles. Faster ones that have more energy will speed up the slower ones, and slower ones will reduce the energy of faster ones just by their interaction. So you can't look at this on an individual particle basis. You have to look at this as a cloud of particles that's moving around that eventually forms an oscillation energy ring. So it, in essence, it sort of works the same way as a normal magnetron, and in other cases it doesn't exactly work the same way. Now, you physics people, you're gonna say, but isotope decays at a certain rate, and this is true. It does decay at a certain rate. And you're going to say, well, it comes off at all angles. Well, yeah, and that's why you'll notice in the picture we have particle deflector rings on the isotope to help keep the isotopes going in the same direction. But we're going to talk about the particles next that come off the isotope. All right, let's talk about cathodes and magnetic fields. A normal hot cathode has electrons that boil off the filament or the filament attachment with tungsten around it. When it heats up, the electrons just, if there's no magnetic field around an electron, it'll come off at any angle there is. But if there's a magnetic field involved, then when that electron boils off the cathode on a hot cathode, then there is an angular moment involved with that. But for some reason, physicists seem to think that with isotope, I have no idea why they think this, they seem to think that when an isotope decays, that it comes off at any angle. But that's not really true, because when the particle decays out of the isotope, it's under the influence of a magnetic field in the magnetron. All right? Same way as a normal magnetron is. A normal magnetron cathode is under the influence of a magnetic field at the point when the particle comes off the cathode. And same way with a cold cathode, a nuclear cathode. The particle is under the influence of the magnetic field when it comes off. So in both cases, the particle may instantaneously come off at any angle, but at the same time, the instantaneous moment has a magnetic field on it. So it's sort of predestined to follow that field. Now, obviously, if it's shooting vertically up, then the particle's, going to go, it's not going to follow the right exact magnetic line. But at the same moment, we have deflectors in there to stop that. And even with a hot cathode, you can have particles coming off in the vertical direction and have the same thing happen, that it doesn't follow it. So it's sort of an assumption on everybody's part that this, this doesn't work the same. When you have an influence, when you have a magnetic field influencing it, it's pretty close to what the hot cathode is too. The cold cathode pretty much acts like the hot cathode also. So, in trying to figure out how many particles are going to do this, you're sort of guessing at this point. So I'm going to cover some more about this cathode stuff. I know you physics people would love to talk about power density versus surface area of an isotope. But that really is a subject all unto itself. It's completely out of the range of the theory of operation here. So that would have to be covered in a different video explaining about that. Let's talk about the cold cathodes some more. One of the things that's very different from a hot cathode is that the isotope produces particles that fall back to the isotope cathode, the cold cathode. The particles that are emitted once the energy is used by the resonators, the particles fall back. And this creates a problem. And if you look down in the left-hand corner of the screen, you'll see a device called a spark gap. So over time, as the particles fall back to the cold cathode, it starts building up a charge. And at some point, the charge will get high enough that it will arc inside the magnetron. So you need a spark gap device hooked to the magnetron to keep the cathode from arcing inside. You don't have this problem with a regular cathode, but you do have it as a problem with a nuclear cathode. And I know some of you are looking there, what is it? It says starter power and voltage and that, and what's all that for? And we're going to sort of cover that next here. But one of the things you do have to have is a spark gap hooked to a nuclear cathode. All right, let's talk about the starter power. What do we need the starter power for? Well, as you put the isotope up into the nuclear magnetron, you're going to possibly charge up the anode. And if the anode voltage is at the same potential as the cathode voltage, then the field won't form inside the magnetron unless you have a tremendous amount of isotope. And you're probably not going to have that. So if you take the power supply that normally runs the magnetron and you hook it up from the cathode to the anode for a couple seconds and turn it on, it'll allow the resonator field to form inside the cavity. And then once the field has formed, the rotational field, then the magnetron will run and create microwaves, and you can turn the starter power off. And you need enough current from the power supply to equal what the current that's coming out of the isotope is. So voltage-wise, it may not be such of a problem, but current-wise, it is a problem, because the more current the isotope produces, the harder it is, to make the thing turn on. So the other thing you need to realize is if you're using positive particles instead of beta particles, the voltage differential has to be turned around. Let's talk about nuclear magnetron history. If you're looking for using a nuclear magnetron in a radar system, it's probably not going to work very well. But if you're interested in using a nuclear magnetron to produce power, then yeah, you're probably going to be able to get it to produce a fair amount of power. There was a prestigious college that had a little bit of a problem. They built one, but they didn't make it that you could remove the isotope from it. And when they got it started, it set off their gamma ray X-ray detector in the lab, and they had to put lead aprons on and go in and rip it apart, because when they tried to shut it off, it wouldn't shut off. So you need to make sure that you have a way of pulling that isotope out of there real quick in case something goes wrong. It's an interesting experiment. It's been done several times. We know it works because it's been done. Don't forget that not only are you dealing with radioactive materials, you're dealing with microwave also, and that can be dangerous also. You got to remember that you have to take that microwave power and put it into something. You can't just make microwave and send it into the air. That's dangerous also. So from a power perspective, converting the microwave power back to normal power, some kind of DC level, why? Yeah, this is a real good way to do power conversion when you're talking about nuclear particles and that type of thing. So it works. It's been tested. The efficiencies are a lot higher than what the mathematics show it to be. So it's is it green energy? It's sort of green energy. We've got probably 200 years worth of nuclear isotope that we could use to make power for the entire United States. We probably got enough isotope that we could refine to run the whole United States for 200 years without ever having to pay for power.